Okay, hi all. Welcome to my presentation, how we got Doom running on Zephyr, and hopefully you guys can all try it or even replicate it. So, introduction by myself. I work for NXP. Mostly I'm working in mobile robotics, so autonomous rovers, drones. That's kind of the way I like to play with. And we hope to get Zephyr running there, driving autonomously, mapping, all that stuff. And then differences I'm working on is IMXRT, 95 MCX, and all these systems run Zephyr. But robots are boring, so we like to play games instead. So today, so why did I port Doom? Some basic explanation about the Doom engines, my development environment and the Zephyr simulator, how I got that working. Some introduction about subsystems, display and input particularly, while running Doom on the real hardware instead of the simulator, and some lessons learned. So, why port Doom? Well, mostly I've been doing low-level accelerometers, control stuff. I was like, okay, let's play around with the media subsystems. So I kind of want to learn how to use the display subsystem. You have LVGL, all other cool stuff. And also some kind of input part. And why Doom? Well, Doom runs with everything, but to my surprise, it was not running on Zephyr. So it's like, hey, that's a nice thing to do. Some technical goals. I also want to play around with these native simulator. So instead of using real hardware directly, why not simulate first and then try to deploy? Also want to focus on generic abstraction, so hopefully it can also run on different hardware, which is kind of the power of Zephyr, where you have these abstraction layers, and also play around with joystick and touchscreen input. So quick introduction about Doom. So 26 years ago, it got released under GPIO. And ever since then, there are all these different variants. People added mods. People wanted to have the original experience, or people want to add lots of enemies. But yeah, there are lots of engines, also lots to choose from, which is also a bit of a challenge. If you want to port Doom, I think these are the three best candidates. So you have Chocolate Doom, PrBoom, which this talk is about. And there's also this Doom generic, which is really stripped down. It's very easy to use support, but you also lose some features. PrBoom has some modding, and Chocolate Doom is mostly the original experience. So my development environment. Well, first we have to create our own example application or workspace. Last year, Julia gave a very good presentation on how to set these things up. So my advice is to check that out. But yeah, once we get our own base barebone application running, okay, how can we port the Doom engine? Well, Doom, it needs libc support. Well, we got Pico libc, that's nice. It's also reliant on POSIX, specifically PrBoom, which got ported to Linux and so on. And it also needed SCL2, which is kind of problematic for Zephyr, but luckily we can just replace those hooks with our own hooks. Particularly it's the graphics, the input, the display. Audio I kind of skipped out on. I didn't have hardware with audio. It would still be cool to add that. But for now, let's keep it simple. So how do we set up? Well, we just start with the native simulator, and with Zephyr you can just build it and you can run your Zephyr application on your PC. But the nice part is that we have all these different subsystems. So we can simulate a display, we can simulate GPIO through our keyboard, we can even have a touchscreen, we have our SysTick timer, and it's pretty much all we need to run the full application on your PC, where typically embedded systems, it's kind of hard to simulate part, but it's a very nice setup. I really recommend people playing around with that. Also, the tracing is also nice because we have to play around with timing and memory constraints. So, well, how do we set up? Well, first let's try just setting up the display. So we just have the display example. Zephyr is very nice. We just have these samples with the test display input. We did some overlay to change resolutions. And how do we then integrate this into Doom? Well, first, Doom has all these hooks. So PrBoom, we just have to initialize the display in the pre-init graphics. Doom runs into this 8-bit color mode, which is a bit of a challenge, where typically your displays, or Zephyr doesn't have actually support for this 8-bit mode. I was thinking about adding it, but it's way more complicated than I thought. But we're going to go further that a bit. And then actually each time the Doom engine has a new frame, we just get this finish update, and then our challenge is to get that frame to our display. So actually it was quite easy just to set it up. We can just, should work, yes, we just run the application and we finally got the Doom splash screen. But you know, we cannot play if the input doesn't work. So we just expanded to the input system. And the nice part about Zephyr is that we can just emulate GPIO buttons or just input buttons just with a keyboard. So we can just map the scan codes we have, and then we just make fake GPIO keys, and with that we just get our input events. And then we have to expand the engine to process the key events. So effectively, it's polling. It's not an event-based. Doom just runs each frame, and it just checks what the key state is that. So we just made a hook. We check if the key is up and down, and we just forwarded this to the depose event, which is the Doom function to get the keys in. And actually, we're just implementing this. We can start playing Doom already on our simulator. So yeah, Zephyr already provides a lot to play around with this. So let's try to run it on the real hardware. So at the time I was working with a IMX RT1170, which is way too fast compared to the hardware we had back then. So I have a gigahertz M7 core, I have 2 megabytes of SRAM, external memory already in the LCD controller. Yeah, so it was just pressing West build EVK and worked, which kind of bummed me out because it was just an evening project, 3 evenings, and it was working. It was like, yeah. So, well, I worked at NXP, and then I saw this development kit coming by. It's like, okay, it's M33, 150 megahertz, 512K SRAM. That's a bit of a challenge, but plenty of flash, and it's also actually quite cheap. It's 25 euros. Typically EVKs are way more expensive, so it's a nice board. Well, challenges. Originally in 1996 you need like 4 megabytes of RAM. I only got 512, so that's a bit of a challenge. Flash, I think it says like around 12. I got 10. Well, let's see how far we get. Well, so Doom uses index colors, and back in the day, DOS also had support for that. So we had this color palette, we could load the palette, and the VGA subsystem CRA can work with that. The display I'm using is using RGB 565, so we need 16-bit colors. And that display is 480 by 320. So I have my frame buffer, 150 kilobytes, the expanded frame, double buffering. I only had 51 kilobytes left for Doom. So yeah, that was a bit of a challenge. Well, I'm going to cheat a bit because that screen was a wide screen. So it's like, well, let's keep the original experience. We're going to make it a bit smaller. I can go to 128 kilobytes. And I was thinking, okay, can we maybe just avoid using double buffering? And it turns out, actually, my display is also just external memory, right? So it has its own SRAM. So why not use that as my double buffer? So what we do is actually we kind of reuse the existing buffer. We kind of just expand the line, and while we're transferring, we're just doing the color conversion. It introduces a bit of tearing. It also increases the frame time. Luckily, an M33 of 150 megahertz is fast enough, so we have enough compute time budget, and we don't have enough memory. So this is the trade-off we took. But I pretty much eliminated then the need of this 300 kilobyte for the second frame buffer. Then there's also these lookup tables. So the Doom engine uses fixed point calculations. So back in the day, the Intels didn't have a floating point unit. So it uses all these LUTs, and on startup, it was calculating those. Looking for my resolution, I needed 100 kilobyte of RAM just to have all these lookup tables there. Well, which is unfortunate because I don't have that memory. So there are different ways to do that. So what I did is like, okay, well, our microcontrollers, typically M33 is a Harvard architecture, so actually I also have flash. So if it's a lookup table, why not put it in flash? I can just access from there. And the simulator is also quite useful for that because I can just use the existing code. I didn't have to like write a Python thing to figure out how the lookup table looks like. I just dump the memory and you just make it read-only data. Alternatively, I could also use the floating point unit, but it's still way slower than a lookup table. So why not use the performance boost you get from it? Then the flash constraints. So Doom is very nicely architected where the engine works on its own, but the whole game logic is in this WOT file, where's all the data. So we have the map, sound, texture, game logic. And luckily there is also this shareware WOT, which is way smaller, and also I don't get in legal trouble, because people have to buy it and I have to get it together. So luckily in my case, I could fit it on the external memory, but if people have smaller chips and they want to port it, these are the alternatives. So you have Squashware, which made smaller watts, and there is this crazy project which they ported to an RP2040, which does like on-demand decompressing. So they use the second core to decompress data while rendering. It's kind of crazy. There's a whole write-up about that. But yeah, you also want to have a fun game experience. So I got this ADC joystick, and luckily there's already like a very nice driver in Zephyr that does fully auto calibration of that, and you just get key input. So not much work. Touchscreen, also quite easy. There's already a touchscreen driver. And I could just simulate that and just make my own abstraction. So running on the real hardware. So this is the board, the touchscreen, and it's just running like that. So we got the GPIO as input, we got the joystick, and next to that also made a small touchscreen wrapper. We just calculate the starting point where I release it, and then you can play the game. Well, technical insights. Well, quick induction on how to adapt PrBoom for use with Zephyr. Also, quick introduction where, hey, you can also just develop without hardware. And actually, it's quite useful because graphical bugs, memory, especially just developing with a gigabyte of RAM is way easier than with the 512 kilobytes of RAM. Well, why is Zephyr ideal? Well, we get all these abstractions. I don't have to care about display transfers. This particular hardware is using a parallel interface, 8080, all that stuff. I just do display write, I get the frame, so it's very nice. Input same, you have GPIO input, but you also have your ADC or touchscreen. You can just make a nice abstraction. It should also work on different hardware. Yeah, again, native similar. And also, I like the modularity. So just start with just the screen. I get my screen working. Okay, we can add input. We can also think about maybe sound, maybe multiplayer. It's also on this. And yeah, it's all open. So if people want to get involved, you can try it. I have some ideas I still want to try. So there is some work on Zephyr host support. So we can emulate a keyboard, but it will also be cool to just put a real keyboard in there and actually play the game with that. Also want to get the chance maybe add some audio and yeah, maybe crazy stuff people can think of. Actually, independent of me, a colleague also implemented our FreeMaster tool where they actually do real-time tracing of the system. So that's also on the demo booth. And yeah, try it out, I would say. Yes, there's also this a QR code, and also on our booth, you can get a free Freedom MCX board, which I also use. So if you want to play it around, you can actually get already the hardware if you want. And yeah, any questions?
You say that we can see this live down at the booth?
Yes, yes. So, and then there's also real-time tracing as well. So there's a PC hooked up, shows even the CPU load per function. And also has some nice introspection. You see even the map, the gameplay. So you can even get some extra data there. Yeah.
So a follow-up question to that. What is the highest, or the most used function right now? Like what is at the top of the profiler?
So mostly it's rendering. It's just the whole rendering algorithm. Game state, game logic is not that hard. And then it's also just reading out and mapping the data through the sprites and so on. Yeah.
But you told that you move the load staples to the flash. You detect the performance that and you get to access flash to get the powers.
There is a slight performance hit, particularly this chip. The flash is embedded, so there's like a small in there. Funny enough, the startup time was way faster because before it was like calculating what's there, and now it just, I think it's leaks like 50 milliseconds and just the game starts. So again, it's also a trade-off. Oh, sorry.
How complicated would it to add audio? Because you said your engine was not supported.
The engine supports it is mostly the hardware I have. So I just need to like have some I2S interface added and then pretty much implement the hooks. Unfortunately, I didn't dive into the Zephyr audio system. The Doom audio system, probably it's going to be some old stuff you have to convert. So maybe it could be hard, but I think it's still, it's DOS era audio, right? It's not that high, so yeah. Well, hopefully you guys can all try it or make your own ports. There are different engines also to play around, so that's very cool. Actually, I'm also trying to port Quake now. I need more memory, so that's a bit of a challenge. So, yeah. Well, thank you.